The solar system is usually shown as a flat disk, 8 planets, circling the sun on a neat, tidy plane. It makes for clean diagrams. It's easy to visualize, but it raises an obvious question that most people never think to ask. What's above that disk? What's below it? The answer is more interesting than you might expect, because once you leave the familiar plane of the planets, you enter regions that are vast, mysterious, and largely invisible structures that surround the solar system in every direction and connect us to the larger galaxy in ways that most people have never considered. These aren't empty stretches of featureless darkness. They're filled with ancient ice, charged particles, invisible bubbles, stellar ghosts, and the faint fingerprints of explosions that happened millions of years before our species ever looked up at the night sky. In this exploration, we'll journey outward, above, below, and all around us to uncover what the solar system is truly embedded in. Layer by layer, we'll peel back the simplicity of those textbook diagrams and replace them with something far stranger and far more magnificent. But first, to understand what exists beyond the plane of the planets, we need to understand why that plane exists at all. Everything in the universe spins. It's one of those fundamental tendencies of matter that emerges naturally from the way gravity and angular momentum interact. From the grandest spiral galaxies to the smallest dust devils on a desert plain, rotation is everywhere. And rotation, given enough time and the right conditions, tends to flatten things out. The story of our solar system begins roughly 4.6 billion years ago in a slowly drifting cloud of gas and dust known as a solar nebula. This cloud wasn't a perfectly still, perfectly symmetric object. It was turbulent. Different parts of it moved at different speeds, in slightly different directions. Some regions were denser than others. The whole thing was alive with subtle, chaotic motion. Then something disturbed it. Astronomers believe a nearby supernova, the catastrophic death of a massive star, sent a shockwave rippling through the nebula. That shockwave compressed regions of the cloud, pushing gas and dust together. Gravity did the rest. Once the density in the cloud's core grew high enough, gravitational collapse began. The nebula started falling inward toward its own center of mass. Now, here's where angular momentum becomes critical. Angular momentum is a property of rotating systems, and it's conserved, meaning it can't simply appear or disappear. It can be transferred, but it can't be destroyed. As the nebula collapsed inward, its rotation accelerated. The same way a figure skater pulls their arms in and spins faster, the contracting cloud began to rotate more and more rapidly. That rotation introduced a powerful asymmetry. Gravity pulled the cloud inward equally in all directions, but the rotation created a centrifugal effect, a tendency for material to resist being pulled toward the center along the plane of rotation. Think of it this way. The rotation creates a kind of equatorial bulge, a disk of material that forms perpendicular to the axis of spin. Material above and below the spin axis can fall directly toward the center without fighting that centrifugal resistance. But material in the plane of rotation gets flung outward as it falls inward. The result is that the cloud collapses most readily along its spin axis, flattening out as it does so. The analogy of pizza dough being spun is imperfect but useful. When a pizza maker tosses a ball of dough into the air with a spin, centrifugal force pulls the material outward from the axis of rotation. The dough flattens. The faster it spins, the flatter it gets. The nebula did something very similar, though over millions of years and on an unimaginably larger scale. The result was a broad, flat, rotating disk of gas and dust surrounding a dense, hot, proto-solar core. The young sun formed at the center of this disk, igniting nuclear fusion. Once the core temperature reached approximately 10 million degrees Celsius. Around it, material in the disk clumped together through a process called accretion, small grains of dust colliding and sticking together, slowly building into pebbles, then boulders, then planetesimals, then protoplanets, and finally the 8 planets we know today. Because all of this material formed within the same flat rotating disk, all the planets ended up orbiting in approximately the same plane. We call this the ecliptic, the plane defined by Earth's orbit around the Sun, which closely matches the original plane of the protoplanetary disk. Stand on Earth and look at the night sky, and the planets will always appear along a narrow band that traces this ecliptic. They never wander far from it because they can't. Their orbits are rooted in the geometry of the disk that gave them birth. Not everything is perfectly aligned, of course. Mercury's orbital plane is tilted about 7 degrees relative to the ecliptic, a significant deviation for the innermost planet, likely shaped by gravitational interactions in the solar system's early, chaotic youth. Venus tilts about 3.4 degrees, Mars 1.9 degrees. The gas and ice giants are all within a couple of degrees of the ecliptic as well. But Pluto, reclassified as a dwarf planet in 2006, has an orbital tilt of nearly 17 degrees, a sign that its history involved more chaotic gravitational sculpting than the 8 major planets. Some comets are even more extreme, arriving from directions nearly perpendicular to the ecliptic, like needles driven straight through a vinyl record. Their steep orbital inclinations tell a story about where they came from, a story we'll return to shortly. But for the main planets, the flatness is essentially complete. They all live within a relatively thin, disc-shaped volume of space, orbiting the Sun in the same direction, in nearly the same plane, in a configuration that has been stable for billions of years. And above and below that disk, what lies there? Before we venture above and below, there's a crucial piece of context that changes the picture entirely. The solar system doesn't sit level within the Milky Way. Our familiar flat disk of planets, the ecliptic, is tilted at roughly 60 degrees relative to the plane of the galaxy. This is not a small tilt. This is a dramatic one. If you were to place a model of the solar system inside a model of the Milky Way, the planetary disk would be canted sharply to one side relative to the galactic plane. Why does this matter? Because the directions we call above and below the solar system don't align with the directions that are above and below the galaxy. When you point perpendicular to the ecliptic straight up and straight down from the plane of the planets, you're pointing in a direction that partly faces toward the galactic center and partly faces outward into the galactic halo. This mismatch has real consequences for understanding what surrounds us. It means the solar system moves through the galaxy not like a coin rolling flat on a table, but more like a coin tilted at an angle, cutting through the galactic disk on a diagonal. Our path through the Milky Way is not a flat orbital trajectory hugging the midplane of the galaxy. It's a gently oscillating path that carries us up through the galactic disk, then back down through it, then up again in a slow cosmic wave that plays out over hundreds of millions of years. The Sun orbits the center of the Milky Way at a staggering speed, approximately 515,000 miles per hour, or around 828,000 kilometers per hour. At that speed, it takes roughly 225 to 250 million years to complete one full orbit of the galaxy. This period is sometimes called a galactic year or a cosmic year. Earth's history spans about 18 galactic years. The dinosaurs went extinct less than 1 galactic year ago. In cosmic terms, we are extraordinarily young. As the Sun travels along this immense orbit, it also bobs slowly up and down through the galactic disk, oscillating above and below the galactic midplane approximately every 64 million years. Some researchers have speculated that these oscillations might correlate with periodic increases in comet bombardment, as our changing position relative to dense regions of the galaxy could disturb the outer fringes of the solar system. Whether that speculation is correct remains an open question, but the oscillation itself is well established. So when we ask what lies above and below the solar system, we're asking about directions that are partly transverse to our galactic orbit, and the structures we find there exist not just in the neighborhood of our solar system, but on scales that stretch deep into the galaxy's vast architecture. There is, of course, no true up or down in space. There is no absolute reference frame that gives meaning to those terms universally. But for the purposes of exploring what surrounds us, astronomers conventionally use the ecliptic plane, the flat disk of planetary orbits, as the reference surface. Directions perpendicular to this plane become above and below. It's an arbitrary but practical choice, and it lets us organize the structures that surround us in a way that's intuitive and mappable. With that framework established, let's begin the journey outward. The first major transition in the solar system's outer architecture is the Kuiper Belt, a broad, disc-shaped region of icy objects that extends from roughly 30 AU, where Neptune orbits, out to about 50 AU from the Sunday. 1 AU, or astronomical unit, is the average distance from the Earth to the Sun, about 93 million miles, or 150 million kilometers. The Kuiper Belt, then, occupies a ring of space between 30 and 50 times that distance. The Kuiper Belt is named after the Dutch-American astronomer Gerard Kuiper, who proposed in 1951 that a disk of icy bodies should exist beyond Neptune, left over from the formation of the solar system. Ironically, Kuiper himself thought the region would have been largely emptied by the time it was studied. He didn't anticipate the richness of what we would eventually find there. But the belt now bears his name, and the objects it contains have rewritten our understanding of the outer solar system. The Kuiper Belt is home to hundreds of thousands of small icy objects, sometimes called Kuiper Belt objects, or KBOs, as well as several dwarf planets, including Pluto, Eris, Makemake, and Haumea. These bodies are relics of the solar system's earliest days, frozen fragments that never managed to come together into a full-sized planet, partly due to Neptune's powerful gravitational influence, preventing the material in that region from accumulating. In terms of geometry, the Kuiper Belt is mostly flat. It occupies roughly the same plane as the ecliptic, though with somewhat more spread in inclination than the major planets. It is, in essence, an outer extension of the same flat disk structure that defines the inner solar system. Above and below the belt perpendicular to the ecliptic, there are relatively few KBOs. The flatness persists. But the Kuiper Belt is not the outermost boundary of the known solar system. It's not even close. Beyond its outer edge, the structure of the solar system undergoes a profound transition. The flat disk gives way to something vastly larger and fundamentally different in shape. Before we get there, however, let's pause to examine a region that astronomers have only recently begun to explore in depth, a transition zone, sometimes called the scattered disk. Overlapping with the outer Kuiper Belt and extending well beyond it is a population of objects known as the scattered disk. These are icy bodies that, at some point in the past, came close enough to Neptune or another of the giant planets to have their orbits dramatically altered, scattered outward and upward into highly elongated, highly inclined orbits that carry them far from the ecliptic plane. The scattered disk represents a kind of orbital chaos that exists at the margins of the flat solar system. While the Kuiper Belt is relatively settled and geometrically orderly, the scattered disk is the aftermath of gravitational violence objects that were kicked around by giant planets, their tidy original orbits replaced by wild, looping paths that carry them far above and below the ecliptic. The most famous object associated with the scattered disk is Eris, a dwarf planet roughly the same size as Pluto, but more massive, located at distances that can exceed 97 AU from the Sun at its farthest point. Eris has an orbital inclination of about 44 degrees relative to the ecliptic. It spends much of its long 559-year orbit far out of the plane of the planets, diving above and below the flat disk on a slow, swooping arc. The discovery of Eris in 2005 was the immediate trigger for Pluto's reclassification. Astronomers were forced to confront the fact that if Pluto was a planet, then Eris, larger, more massive, equally far, would also have to be a planet. And if both were planets, then dozens of similarly sized objects likely lurked in the outer solar system, awaiting discovery. Rather than continuously expand the planet list, the International Astronomical Union redefined the term planet to require that an object have cleared the neighborhood of its orbit, a criterion that neither Pluto nor Eris meets. Both were reclassified as dwarf planets. The scattered disk illustrates something important. The transition from the flat inner solar system to the spherical outer regions isn't sharp, it's gradual. As we move outward, orbital inclinations increase. Objects that were once neatly confined to the ecliptic plane are found at greater and greater angles above and below it. The strict flatness of the inner solar system dissolves slowly into a kind of three-dimensional scatter. Eventually, the flat disk ends entirely, and above and below the scattered disk, extending in every direction, begins one of the most extraordinary structures in planetary science. Imagine standing at the center of a soap bubble. The inner surface of the bubble surrounds you in every direction, above, below, left, right, in front, behind. Now imagine that bubble is made not of soap film, but of trillions of frozen objects, each one a silent relic from the solar system's violent birth. Each one tracing an immense, slow orbit that carries it over thousands or millions of years through the deepest cold and darkness imaginable. That is the Oort cloud. The Oort cloud is the outermost region of the solar system, a vast, roughly spherical shell of icy bodies that surrounds everything else we've discussed. Unlike the Kuiper belt and the scattered disk, it is not flat. It is not confined to the ecliptic plane or anywhere near it. It extends above, below, and in every other direction from the Sun, enveloping the entire solar system in a nearly perfect sphere of frozen debris. Its scale is almost impossible to meaningfully comprehend. The Oort cloud is thought to begin at somewhere around 2000 AU from the Sun, already far beyond anything we've sent probes to, and extends outward to perhaps 100,000 AU or more. Neptune, the outermost planet, orbits at about 30 AU. The Voyager 1 spacecraft, the most distant human-made object ever launched, crossed the heliopause at around 123 AU and is currently travelling at about 150 AU from the Sunday. It is moving at roughly 38,000 miles per hour. At that speed, it would take approximately 300 years just to reach the inner edge of the Oort cloud and another 30,000 years to pass through it. The outer edge of the Oort cloud sits approximately a quarter to a third of the way to the nearest star system, Alpha Centauri, located about 268,000 AU away. In light years, the Oort cloud extends to about 1.5 to 2 light years from the Sunday. Our nearest stellar neighbour is about 4.24 light years away. The space between the Oort cloud and the next star is deep, cold, and almost perfectly empty, but it's not infinite. The Oort clouds of neighbouring stars may actually overlap or come close to touching. The Oort cloud is thought to contain trillions of individual objects. Estimates range from several billion to several trillion, most of them small icy bodies composed primarily of water, ice, carbon monoxide, carbon dioxide, methane, ammonia, and various other frozen volatiles. Some may be larger, perhaps the size of small dwarf planets, though none have been directly confirmed at those distances. These objects are spread so thinly across such an enormous volume of space that the Oort cloud is, despite its staggering population, almost inconceivably empty on average. The typical distance between objects is vast, far too large to cause collisions or even close gravitational interactions under normal circumstances. Why is the Oort cloud spherical while the Kuiper belt is flat? The answer lies in history. The icy bodies of the Oort cloud didn't form where they are now. They formed much closer to the Sun, in the same flat protoplanetary disk that gave birth to everything else. But early in the solar system's history, the giant planets, particularly Jupiter and Saturn, were gravitational titans, flinging smaller icy bodies outward through slingshot interactions. Many of these objects were ejected entirely from the solar system, but others were kicked into enormously elongated orbits that carried them far out beyond the planetary region. At such extreme distances, the gravitational influence of the Sun, while still real, is exceedingly weak, and at those distances, other gravitational influences begin to matter. The combined tidal gravitational pull of the Milky Way galaxy itself slowly torques the orbits of these distant icy bodies. So does the gravitational influence of passing stars over billions of years? Countless stars have drifted close enough to the outer solar system to gravitationally nudge the orbits of Oort cloud objects. These weak but persistent perturbations, acting over billions of years, randomized the orbital inclinations of these objects, spreading them out of the ecliptic plane and distributing them uniformly in all directions. A flat disk became a sphere. We have never directly observed the Oort cloud. No telescope currently in operation is powerful enough to detect individual Oort cloud objects at those distances. We can't see them. They're too small, too cold, too far away, and too dark. The blackness of space at those distances is nearly total. The Sun, seen from the outer Oort cloud, is just an unusually bright star, indistinguishable to the naked eye from any other. Yet, we know the Oort cloud exists. The evidence is written in the orbits of comets. Comets come in two broad categories: short-period comets, which orbit the Sun in less than 200 years, and typically have relatively flat orbits originating from the Kuiper belt and scattered disk, and long-period comets, which have orbital periods of more than 200 years, sometimes thousands, sometimes millions of years, and arrive from all directions, not just from near the ecliptic plane. It is these long-period comets that betray the existence of the Oort cloud. Their orbits, when traced backward, originate from random directions in the sky above, below, and all around. There is no preferred plane, no preferred direction. The distribution is spherical, and the only structure that could produce a spherical distribution of comet source regions is a spherical cloud of icy objects surrounding the solar system in every direction. The mechanism by which Oort cloud objects become comets is also well understood in its broad strokes. Over the billions of years since the solar system formed, occasional gravitational perturbations from a passing star, a wandering rogue planet, or the subtle tidal pull of the galactic disk can nudge an Oort cloud object out of its stable distant orbit. If the perturbation is strong enough, the object is deflected inward, falling toward the inner solar system on a long, swooping trajectory that takes thousands or millions of years. As it approaches the Sun, solar radiation heats its icy surface, vaporizing frozen gases and releasing trapped dust into a glowing coma and tail the classic appearance of a comet. Some of these long-period comets are among the most spectacular objects ever seen in the night sky. Comet Hale-Bopp, which dazzled observers in 1997, is estimated to have an orbital period of roughly 2,530 years. Comet Hyakutake, visible around the same era, had an orbital period estimated at tens of thousands of years. Comet West, visible in 1976, may have had an orbital period of several 100,000 years. These objects spent the vast majority of their existence in the deep cold of the Oort cloud, drifting silently in nearly perfect darkness before a subtle nudge sent them on their long fall toward the warmth of the inner solar system. The Oort cloud, then, is not merely a curiosity of the outer solar system. It is a direct window into the solar system's primordial past, a deep frozen archive of the material that existed during and immediately after the formation of the planets. If we could ever reach out and sample those objects directly, we would be holding in our hands the most pristine material in the solar system, chemically unchanged since the dawn of the planetary system 4.6 billion years ago. Step back now from the vast and hypothetical reaches of the Oort cloud and return to something more concrete, something that has actually been physically traversed by human-made machines. Surrounding the solar system in every direction, including above and below the ecliptic plane, is a dynamic protective structure created entirely by the Sun itself. It's called the heliosphere, and understanding it requires understanding the solar wind. The Sun does not simply sit quietly at the center of the solar system, radiating light and heat in every direction. It also continuously exhales. The Sun's outer atmosphere, the corona, reaches temperatures of several million degrees Celsius, far hotter than the Sun's visible surface at roughly 5,500 degrees Celsius. At those extraordinary temperatures, particles in the corona gain enough energy to escape the Sun's gravity entirely, streaming outward in all directions at speeds of 300 to 800 kilometers per second. This continuous stream of charged particles, mostly protons and electrons, is the solar wind. The solar wind doesn't simply flow outward and then stop. It expands continuously in all directions, growing thinner and slower as it travels. But it doesn't stop at any neat, predefined boundary. What eventually stops it is a confrontation with the interstellar medium, the thin gas, dust, and magnetic fields that fill the space between stars. As the solar wind flows outward, it eventually reaches a region where it must decelerate to subsonic speeds in order to ram against the interstellar medium. This transition region is called the termination shock. Voyager 1 crossed the termination shock in 2004 at a distance of roughly 94 AU from the Sunday. Voyager 2 crossed it in 2007 at a slightly closer distance of about 84 AU. The fact that the two spacecraft crossed the termination shock at different distances tells us that the heliosphere is not a perfect, symmetric structure. It varies with direction. Beyond the termination shock lies the heliosheath, a turbulent transition zone where the decelerated solar wind mingles and struggles against the oncoming pressure of the interstellar medium. This region is chaotic and complex, filled with magnetic field reversals, particle heating, and turbulence. Think of it as the buffer zone between the solar system's own environment and the interstellar environment outside. The outer boundary of the heliosheath, where the solar wind's influence finally gives way entirely to the interstellar medium, is called the heliopause. This is the true edge of the heliosphere, the point beyond which the Sun's solar wind no longer holds sway. Voyager 1 crossed the heliopause in August 2012 at a distance of approximately 121 AU from the Sunday. This was a historic moment, humanity's first confirmed contact with interstellar space. Voyager 2 followed in November 2018, crossing the heliopause at about 119 AU. Both spacecraft are now traveling through interstellar space, sending back data that is fundamentally different from anything collected within the solar system. The data from both voyages revealed that the interstellar medium beyond the heliopause is denser, cooler, and carries a different magnetic field orientation than the solar environment within. The transition was surprisingly sharp, more like a boundary than a gradual fade. But the heliosphere has an overall shape that's worth examining carefully, because it's not a sphere. The solar system is moving through the galaxy at hundreds of thousands of miles per hour, and that motion means the solar wind is not just expanding into a static environment, it's expanding into an oncoming wind of interstellar material. The result is that the heliosphere is compressed on the leading side of our galactic motion, the upstream direction called the helionose, and stretched out into a long tail on the trailing side, sometimes called the heliotail. The shape that results is something like a comet, which is fitting since a comet's shape is created by the same interplay between a streaming medium and the pressure of oncoming flow. The heliosphere is, in a sense, the solar system's own comet tail, streaming behind us as we travel through the galaxy. Think of the analogy of a boat moving through water. At the bow, the water is compressed into a wave. Behind the boat, a wake stretches outward, carrying the turbulence of the passage. The heliosphere works similarly, but instead of water, it's plasma, and instead of a boat, it's an entire star system. Recent data from the IBEX spacecraft, the Interstellar Boundary Explorer, has refined our picture of the heliosphere's shape significantly. IBEX observes the heliosphere indirectly by detecting energetic neutral atoms that are produced when fast solar wind particles interact with the slow interstellar medium. The patterns these atoms create reveal the structure of the heliosheath and heliopause in ways that direct spacecraft traversal cannot. The data suggests the heliosphere may be more like a crescent shape, or perhaps even more complex, with the heliotail not extending perfectly straight behind us, but curving in response to the heliospheric magnetic field. There may also exist a structure upstream of the heliopause called the bow shock, a boundary where the interstellar medium transitions from supersonic to subsonic flow as it encounters the heliosphere. Whether a true bow shock exists is still debated. Some models suggest the interstellar medium is not flowing fast enough relative to our heliosphere to form a true bow shock, and instead a more gradual transition called a bow wave occurs. The heliosphere's influence extends above and below the ecliptic plane, just as it extends in all other directions. In the perpendicular directions above and below the heliosphere, extends outward to distances comparable to its extent in the ecliptic plane, though the exact dimensions vary. In the direction toward the leading edge of our galactic motion, the heliosphere is compressed to perhaps 80 to 100 AU. In the trailing direction, the heliotail may extend thousands of AU. What the heliosphere provides at a fundamental level is protection. The interstellar medium contains galactic cosmic rays, high-energy particles accelerated by supernovae and other energetic events in the galaxy. These particles can damage DNA and increase mutation rates in living organisms. The heliosphere deflects or attenuates a significant fraction of these incoming cosmic rays, providing a partial shield that helps maintain the biological environment on Earth. Without the heliosphere, the cosmic ray flux at Earth's surface would be significantly higher, with consequences for life that are still not fully understood. The Sun's activity is not constant, and neither is the heliosphere. During periods of high solar activity, solar maximum, when sunspot numbers peak, and solar flares and coronal mass ejections are most frequent, the solar wind is stronger and denser, expanding the heliosphere and providing more robust shielding. During solar minimum, the heliosphere contracts slightly. These breathing cycles of the heliosphere occur on an 11-year timescale tied to the solar magnetic activity cycle. Over much longer timescales, millions and billions of years, the sun's luminosity and solar wind output have changed significantly. In the distant past, the young sun emitted less light but potentially a stronger solar wind. In the future, the sun will gradually brighten and eventually swell into a red giant, dramatically changing or destroying the heliosphere entirely. The solar system's protective bubble is not eternal. It is a feature of a particular moment in our star's long life. Step outside the heliopause, cross the boundary into interstellar space, and you might expect to find empty vacuum. In a sense, you'd be right. Interstellar space is extraordinarily empty by any human standard. The density of matter in the interstellar medium is typically less than 1 atom per cubic centimeter. Compare that to the air you're breathing right now, which contains approximately 27 quintillion molecules per cubic centimeter, and the interstellar medium is effectively a vacuum beyond anything achievable in a laboratory on Earth. But it is not a perfect void. The interstellar medium is not uniform. It has structure. It has regions of different density, temperature, and composition shaped over billions of years by the births and deaths of stars, the shockwaves of supernovae, the magnetic fields that thread through the galaxy. The space through which our solar system is currently traveling is part of a particular region called the local interstellar cloud. The local interstellar cloud, sometimes called the local fluff, is a region of slightly denser, slightly warmer interstellar gas, mostly hydrogen and helium, that the Sun is currently passing through. It extends roughly 30 light-years across in some directions, and our solar system has been traveling within it for approximately 60,000 to 150,000 years. In another 10,000 to 20,000 years, we may exit the local interstellar cloud entirely and enter a different region of the interstellar medium. The temperature of the gas in the local interstellar cloud is estimated at around 6,000 degrees Celsius, quite warm by interstellar standards. Though remember that this figure refers to the kinetic energy of individual particles, not to any macroscopic experience of warmth. The density is so low that this hot gas contains almost no thermal energy in practical terms. You could not detect it with your skin, but it does interact with the heliosphere, pressing against the heliopause and shaping its form. The local interstellar cloud is not flat. It extends above and below the ecliptic plane in 3 dimensions. It is, in its own way, one of the first truly 3-dimensional structures we encounter once we step outside the solar system's own protective bubble. It is neither aligned with the ecliptic nor with the galactic plane. It is simply a cloud of gas drifting through the galactic environment on its own trajectory. The Sun's motion through the local interstellar cloud is not random in the galactic context. The Sun and the cloud are both orbiting the center of the Milky Way, and the relative velocity between the Sun and the local interstellar cloud is relatively small, on the order of 26 kilometers per second. This means that although the Sun is moving through the cloud, it's doing so slowly relative to the enormous distances involved. The cloud has been a feature of our immediate interstellar environment for thousands of centuries. The local interstellar cloud itself is part of a larger structure called the Local Interstellar Medium Complex, or Local Cloud Complex, which encompasses several neighboring clouds of gas drifting through the same general region of the galaxy. The G cloud, the Blue cloud, the Hour cloud, each one is a slightly different patch of interstellar material, with its own density, temperature, and velocity characteristics. As the Sun continues its orbit of the galaxy, it will move through different patches of this complex, potentially experiencing periods of higher or lower interstellar pressure against the heliosphere. There is evidence that our Sun has passed through much denser interstellar clouds in the past regions, dense enough that the heliosphere would have been dramatically compressed, perhaps to distances even within the orbit of Saturn. In such periods, the inner planets, including Earth, would have been directly exposed to the interstellar medium, to galactic cosmic rays, and to the gas and dust between the stars. What consequences such exposures might have had for life on Earth, or for the chemistry of our atmosphere, is an active area of research and speculation. The local interstellar cloud, above, below, and all around the solar system, is therefore not merely an ambient backdrop. It is a dynamic environment through which we are constantly moving, and through which we have moved in very different conditions throughout the history of the solar system. Zoom out further, step back until the local interstellar cloud is just a small feature in a much larger landscape. And there it is, one of the most remarkable structures in our galactic neighborhood, a structure that the solar system has been embedded in for millions of years. The local bubble. The local bubble is an enormous region of unusually low-density space, roughly 1,000 light-years across, within which our solar system currently resides. It is not empty. No region of space this size is truly empty. But the density of matter within the local bubble is significantly lower than in the surrounding galactic disk, whereas the typical density of interstellar matter in the Milky Way might be a few tenths of an atom per cubic centimeter. The interior of the local bubble contains on the order of 0.005 to 0.01 atoms per cubic centimeter, roughly 10 to 100 times less dense than average. The local bubble is, in the most vivid sense, a cosmic void carved out of the galactic fabric, a vast cavity in the interstellar medium, surrounded by walls of denser material, stretching above and below the galactic midplane for hundreds of light years. How was it formed? The answer is spectacular and violent and ancient. Astronomers believe the local bubble was carved by supernovae, the catastrophic deaths of massive stars, explosions so powerful that a single one can, for weeks, outshine an entire galaxy of hundreds of billions of stars. Over the past 10 to 14 million years, it is estimated that approximately 14 to 20 individual supernovae exploded within what is now the local bubble region. These weren't random, isolated events. They were part of a cluster of massive stars that formed together, lived briefly and brilliantly, and then died in rapid sequence. When a massive star explodes as a supernova, it releases an almost incomprehensible amount of energy, roughly 10 to the power of 44 joules, most of it in the form of neutrinos, but a significant fraction as kinetic energy in the expanding shockwave. This shockwave slams outward into the surrounding interstellar medium at thousands of kilometers per second, sweeping up gas and dust like a cosmic snowplow. The explosion doesn't just destroy the star, it reshapes the interstellar landscape around it for hundreds of light years in every direction. 14 to 20 of these explosions, occurring over millions of years in the same general region of the galaxy, would have progressively swept out and inflated a cavity of low-density gas, pushing material outward and compressing it into dense shells at the expanding boundary. Each supernova added to the work of the previous ones, enlarging and reinforcing the bubble. The hot, thin, X-ray emitting gas that fills the local bubble today is the residue of these ancient explosions' plasma that was shock heated to millions of degrees and has since been slowly cooling over millions of years. The solar system wasn't always inside the local bubble. Our path through the galaxy carried us into this region approximately 5 to 10 million years ago, long before modern humans existed, but well within the period of hominid evolution on Earth. Before that, we occupied a different region of the interstellar medium, with different density and different cosmic ray environment. The entry into the local bubble may have had subtle consequences for Earth's climate and for the cosmic ray flux reaching the planet's surface, though these potential effects are still being studied. We have physical evidence embedded in the Earth itself that corroborates this journey. Deep sea sediments collected from the ocean floor contain microscopic grains that carry elevated levels of iron. 60, a radioactive isotope of iron that is not produced in significant quantities by any process on Earth or in the ordinary solar system, but which is produced in the thermonuclear furnace of a supernova explosion. The detection of elevated iron 60 inches sediments deposited approximately 2 to 3 million years ago and also around 6 to 7 million years ago aligns remarkably well with the predicted timing of our solar system's passage through the shell of the local bubble and with the estimated times of the most recent supernovae that contributed to the bubble's formation. These iron atoms travelled from the hearts of dying stars across hundreds of light years of empty space, through the solar system, through Earth's atmosphere, and settled gently onto the ocean floor, where they were incorporated into the sediment record. They are, in a very literal sense, stellar ash physical residue of the cosmic catastrophe that shaped the space we now inhabit. When oceanographers drill cores from the sea floor and study the geochemical record, they are also, whether they intend to or not, reading the history of the solar system's journey through the galaxy. The walls of the local bubble, the compressed shells of gas and dust at its boundaries are not static. They are the sites of active and ongoing star formation. The pressure of the bubble's shockwaves compressed the material swept up at its edges to densities high enough to trigger gravitational collapse. New stars, including potentially stars with planetary systems not entirely unlike our own, are forming today in the dense molecular clouds at the local bubble's boundary, tens and hundreds of light years above, below, and around us. Some of the most well-known star-forming regions in the night sky are located at or near the walls of the local bubble. The Ophiuchus star-forming region, the Perseus molecular cloud, the Taurus and Chameleon star-forming regions all lie near the boundary of the local bubble at distances of a few hundred light years. The Orion molecular cloud complex, home to the famous Orion Nebula, lies just beyond the bubble's edge at about 1,300 light years. These regions, visible on clear nights as faint nebulosity or as dense, dark patches against the background of stars, are the birthplaces of future solar systems, and they exist where they are, at least in part, because the ancient supernovae that carved the local bubble compressed the interstellar material that will become tomorrow's stars. The local bubble has recently been mapped in unprecedented three-dimensional detail using data from the Gaia Space Telescope, which has measured the positions and properties of more than 1 billion stars with extraordinary precision. The three-dimensional dust map, derived from Gaia data, reveals the local bubble's walls in striking spatial detail, not a perfect sphere, but an irregular, somewhat squashed cavity, elongated in certain directions and compressed in others by the complex gravitational and pressure environment of the galactic disk. The solar system sits well inside the local bubble's interior, roughly centered within it, though not precisely at its geometric center. Above and below us, within the reference frame of both the ecliptic and the galactic plane, the bubble extends for hundreds of light years before its walls are reached. We are, in a profound sense, floating inside a cosmic room carved by stellar deaths, surrounded by ancient shockwave residue bounded by walls of active starbirth and embedded in a rarefied sea of hot, slowly cooling plasma. The local bubble changes our understanding of the solar system's cosmic context in a fundamental way. We are not in an average region of the galaxy. We are in an unusually empty, unusually hot, unusually rarefied region that was specifically sculpted by a sequence of rare, catastrophic events. The fact that we can study the galaxy from within this cavity, with its relatively clear lines of sight, compared to denser regions of the galactic disk, has influenced everything from our observations of the cosmic microwave background to our understanding of the distribution of nearby stars. In a subtle way, the bubble may have shaped not just our environment, but our ability to observe and understand the universe itself. To fully appreciate what lies above and below the solar system, we need to understand the structure of the environment that contains everything we've discussed so far. The Oort cloud, the local bubble, the local interstellar cloud, all of these structures exist within a far grander architecture. They are features of the Milky Way galaxy, and specifically of one particular region within it. The Milky Way is a barred spiral galaxy. That designation carries a great deal of meaning packed into just 4 words. It is a galaxy, a gravitationally bound system of stars, gas, dust, and dark matter. It is spiral, meaning it has long curved arms of star formation and stellar density that wrap outward from a central region like the arms of a cosmic pinwheel. And it is barred, meaning its center is not a simple point or sphere of concentrated stars, but rather an elongated bar of densely packed stars from which the spiral arms emerge at both ends. The Milky Way contains somewhere between 100 billion and 400 billion stars, though the uncertainty in that estimate reflects the genuine difficulty of counting objects in a system you are physically embedded within. We cannot step outside the galaxy and survey it from a distance. Everything we know about its large-scale structure has been inferred indirectly through painstaking observations of stellar positions, velocities, chemical compositions, and distributions, combined with our understanding of how galaxies form and evolve. In this sense, mapping the Milky Way is a bit like trying to draw a map of a city you've never seen from above, using only the information you can gather while walking through its streets. The galaxy's disk, the flat, rotating structure in which most of its stars reside, is approximately 100,000 light-years in diameter, though some studies have suggested it may extend somewhat farther, perhaps to 120,000 or even 200,000 light-years. Its thickness varies, but in the region where the Sun resides, the thin disk, the densest, most active, most recently star-forming component, is roughly 1,000 to 1,500 light-years thick. Surrounding this thin disk is a thicker, older, less dense population of stars called the thick disk, which extends to perhaps 3,500 light-years above and below the galactic midplane. The Sun's position within this disk is notable for a few reasons. We are located approximately 26,000 light-years from the galactic center, roughly halfway between the center and the outer edge of the disk. We sit between 2 of the galaxy's spiral arms, between the Sagittarius arm, which lies closer to the galactic center, and the Perseus arm, which lies farther out. Our local region is sometimes described as a minor spur or bridge between these arms, called the Orion Arm or the Orion Spur, a smaller, shorter segment of star-forming activity that connects the 2 major arms in our part of the galaxy. The Sun's position above or below the galactic midplane is also interesting. The galactic midplane is the geometrical center of the disk, the surface of symmetry around which stellar density peaks. The Sun is currently located approximately 56 light-years above the galactic midplane, slightly north of center in astronomical convention. This is well within the thin disk, not near its upper or lower edge. But, as noted earlier, the Sun doesn't stay at this height forever. Its orbit around the galactic center is not a perfect flat circle. It oscillates slowly up and down through the disk, crossing the midplane approximately every 30 to 35 million years, reaching maximum heights of perhaps 230 to 260 light-years above or below the midplane before gravity pulls it back. This gentle bobbing motion has been going on throughout the Sun's life, and it will continue for billions of years into the future. These oscillations have potential consequences that extend beyond mere positional bookkeeping. As the Sun rises above or descends below the galactic midplane, it passes through regions of varying stellar density, interstellar gas density, and cosmic ray intensity. Near the midplane, where stellar density peaks, gravitational perturbations from passing stars are more frequent. Above and below the midplane, the stellar environment is sparser, but the cosmic ray environment may be different in subtle ways. The galactic disk is where nearly all of the Milky Way's star formation occurs. Stars form in dense molecular clouds, cold, dark regions of the interstellar medium where hydrogen gas has condensed to high enough densities to begin gravitational collapse. These clouds are concentrated in the spiral arms and in the denser regions of the disk. Above and below the disk, star formation is much rarer, and the stellar environment transitions from the active, metal-rich thin disk to the older, more quiescent populations of the thick disk, and eventually to the galactic halo. The disk is not a serene, stable structure. It is dynamic, turbulent, and perpetually shaped by the forces acting upon it. Supernova explosions continuously inject energy into the interstellar medium, driving shockwaves, heating gas, and launching material above and below the midplane in fountains of hot plasma that can reach heights of several thousand light-years before cooling and falling back down. The magnetic field of the galaxy threads through the disk in a complex, tangled structure. Giant molecular clouds collide, compress, and form new generations of stars. The disk is alive in ways that static diagrams can never adequately convey. Understanding the disk gives us the context we need to appreciate what lies above and below it, the vast, ancient, three-dimensional architecture of the galactic halo. Above and below the galactic disk, far above and below, far enough to leave behind the disk's flat, busy, star-forming structure, the Milky Way doesn't simply end. Instead, it transitions into a different kind of structure entirely, the galactic halo. The galactic halo is roughly spherical, enveloping the disk on all sides above, below, and extending outward well beyond the disk's diameter. It is vast. The stellar halo, defined by the distribution of stars within it, extends to distances of perhaps 100,000 to 200,000 light-years from the galactic center, comparable to, or even larger than, the diameter of the disk itself. Some definitions of the halo include even more distant structures, extending the halo's effective radius to 300,000 light-years or more. The dark matter halo, which we'll discuss shortly, is thought to extend much farther still. The stellar component of the halo is sparse. If the galactic disk is a crowded city, the halo is the countryside surrounding it, vast in extent, but with enormously lower population density. The stars of the halo are spread so thinly that, on average, the distances between individual halo stars are vastly greater than the distances between disk stars. Night skies, as seen from a hypothetical planet orbiting a halo star, would be dramatically darker and less populated than our own fewer nearby stars, fewer stellar clusters. and far less of the diffuse glow of the galactic disk overhead. But the halo stars that do exist tell a remarkable story. They are old, extraordinarily, almost incomprehensibly old. Halo stars are among the oldest objects in the observable universe, with ages reaching back to 12 to 13.5 billion years formed when the universe was less than a billion years old, in the first chaotic epoch of galactic assembly. They formed before the Milky Way was the disc-shaped galaxy it is today. They formed when galaxies were still in the process of collapsing, merging, and taking shape, when the universe was a far denser, far more violent place than it is in our current cosmic epoch. These ancient stars differ chemically from younger disk stars, like the Sun, in ways that reflect the different conditions of their formation. They are metal-poor in astronomical terminology. Metals refers to all elements heavier than hydrogen and helium, and metal-poor stars are those with very low abundances of these heavier elements. This low metallicity is a direct signature of their age. The very first stars in the universe formed from hydrogen and helium almost exclusively, because the heavier elements had not yet been synthesized. It took generations of stellar nuclear fusion and supernovae to build up the carbon, oxygen, iron, silicon, and other heavy elements that are abundant in younger stars like the Sunday halo stars. Having formed when the universe was young and the interstellar medium was still nearly pristine, carry the chemical signature of that early epoch. They are relics of a universe that no longer exists, frozen records of conditions that prevailed when our galaxy was being assembled from the mergers of smaller proto-galactic fragments. The orbits of halo stars are also strikingly different from disk stars. Disk stars, like the Sun, orbit the galactic center in roughly circular orbits, all moving in the same direction, in the same general plane, like well-ordered traffic on a cosmic freeway. Halo stars, by contrast, orbit the galactic center in all manner of directions, some prograde, some retrograde, some at steep angles to the disk. Their orbits are highly eccentric, carrying them on long, looping paths that plunge deep toward the galactic center and then swing far out into the outermost regions of the halo. There is no single preferred direction or plane for halo star orbits. The distribution is three-dimensional and nearly isotropic. This chaotic distribution of orbits is not a mere curiosity. It is, once again, a record of history. The random orbital directions of halo stars reflect the conditions under which they formed in smaller proto-galactic fragments that were later incorporated into the growing Milky Way through mergers and accretion. Each stream of similarly moving halo stars, when identified and traced, can potentially be linked to a particular dwarf galaxy or proto-galactic fragment that was consumed by the Milky Way billions of years ago. The Milky Way's stellar halo is, in this sense, an archaeological record of galactic cannibalism. The accumulated stellar populations of dozens or hundreds of smaller galaxies that were gravitationally captured and disrupted over billions of years. Among the most spectacular inhabitants of the galactic halo are the globular clusters' dense, spherically symmetric collections of tens of thousands to millions of stars, gravitationally bound into tight, brilliant balls of light. The Milky Way is host to approximately 150 to 200 known globular clusters, scattered throughout the halo in all directions above and below the galactic disk. They orbit the galactic center on elongated, often highly inclined paths, spending most of their time in the sparse outer regions of the halo, but occasionally swinging inward toward the disk and bulge. From the perspective of an observer in the inner Milky Way, globular clusters appear scattered across the sky in all directions, concentrated somewhat toward the galactic center, but present above and below in roughly equal numbers. consistent with their halo distribution. Globular clusters are ancient. The oldest known globular clusters have ages of 12 to 13 billion years, making them among the oldest objects in the universe. They formed in the earliest epochs of galactic assembly, when conditions in the proto-galactic environment were dense enough to trigger the formation of millions of stars in tight, compact regions. Whatever process created them, and this is still not fully resolved in astrophysics, globular clusters have survived for nearly the entire age of the universe, slowly losing stars to gravitational interactions and tidal forces, but remaining gravitationally coherent across timescales that dwarf the entire history of complex life on Earth. Inside a globular cluster, the stellar environment is almost unimaginably different from our own neighborhood. The stars are packed so densely that the average distance between them might be measured in fractions of a light year rather than in light years. Night skies, as seen from planets within a globular cluster, if such planets exist in significant numbers, which is uncertain given the cluster's low metallicity and the gravitational chaos of the dense environment, would be blazing with stars. The entire sky would be brilliant, not just the plane of a galaxy. Stars in all directions, above and below the local plane, north and south, east and west, at distances close enough to show as disks of light rather than points. Our night sky from Earth gives us some sense of this. When we look toward the galactic center in the direction of Sagittarius, we are looking toward the region where globular clusters are most concentrated, and on dark nights away from city lights, the sky in that direction is visibly richer, more densely packed with stars. But even our richest skies are pale shadows of what a globular cluster interior would look like. The distribution of globular clusters throughout the halo has been instrumental in revealing the structure of the galaxy itself. In the early 20th century, the American astronomer Harlow Shapley used the positions and distances of globular clusters to determine the size of the Milky Way and the Sun's position within it. Before Shapley's work, many astronomers believed the Sun was near the center of the galaxy. Shapley showed, by mapping the distribution of globular clusters which are symmetrically distributed around the true galactic center, that the Sun is in fact far from the center in an outer region of the galactic disk. It was a revelation of profound philosophical importance. Not only is Earth not the center of the solar system system is not the center of the galaxy. We are located in the galactic suburbs, far from the dense energetic core, in a relatively quiet region of a vast rotating disk. The galactic halo contains another class of structures that have only been fully revealed in the era of precision astrometry, the ability to measure the positions, distances, and motions of stars with extraordinary accuracy. Stellar streams are elongated ribbons of stars spread out along the orbital paths of disrupted stellar systems. They form when a smaller stellar system, a globular cluster, or a dwarf galaxy is captured by the Milky Way's gravity and gradually stretched and torn apart by tidal forces. As the smaller system orbits within the Milky Way's gravitational field, stars at the leading edge of the orbit experience slightly more gravitational pull than stars at the trailing edge. This differential force, the tidal force, slowly peels stars away from the smaller system and distributes them along two streams, one leading the parent object in its orbit and one trailing behind it. Over hundreds of millions of years, a tidally disrupted system can be completely dissolved, leaving behind nothing but a thin ribbon of stars, a stellar stream that traces the original orbital path of the parent object through the galaxy. These streams extend above and below the galactic disk, arcing through the halo on the elongated orbits of their disrupted parent systems. The Sagittarius stream is one of the most dramatic examples. It is the remnant of the Sagittarius dwarf elliptical galaxy, a small galaxy that is currently in the process of being consumed by the Milky Way. The Sagittarius dwarf galaxy, discovered in 1994, is located on the far side of the Milky Way's disk from Earth, at a distance of about 65,000 light-years. It is being torn apart by the Milky Way's tidal forces, and streams of its stars now wrap nearly completely around the Milky Way great arcs of stars, sweeping above and below the galactic disk, extending over more than 1,000 degrees of sky when traced across the entire celestial sphere. These streams are among the most striking evidence that the Milky Way has grown to its current size through the consumption of smaller galaxies. They are the scar tissue of galactic mergers, evidence of cosmic violence written in the positions and velocities of millions of individual stars. The Gaia Space Telescope has transformed our understanding of stellar streams in the Milky Way. Before Gaia, only a handful of streams were known. Gaia's precise measurements of the motions of over 1 billion stars have revealed dozens of previously unknown streams, thin, faint ribbons of stars moving coherently through the halo, each one a story of disruption and dissolution that played out over billions of years. Some of these streams likely originate from globular clusters. Others almost certainly represent the remains of dwarf galaxies that fell into the Milky Way in the distant past. A few may trace the orbits of systems so ancient and so thoroughly disrupted that no recognizable parent object remains. All of them extend through the halo above and below the galactic disk, painting the three-dimensional structure of the Milky Way's history in the motions and positions of its stars. We have traveled from the flat plane of the planets, through the icy shell of the Oort cloud, across the heliosphere's protective boundary, through the rarefied interior of the local bubble, upward through the galactic disk and into the ancient, sparse stellar halo. At each step, the structures we've encountered have grown larger and older, but we have not yet encountered the dominant component of the galaxy. We have not yet addressed the substance that makes up the majority of the Milky Way's mass, that holds it together against the centrifugal force of its own rotation, and that extends above and below the galactic disk to distances dwarfing everything else we've discussed. We have not yet addressed dark matter. Dark matter is one of the most extraordinary and troubling concepts in modern science. It is matter in the sense that it has mass and therefore gravitational influence. But it is dark in the sense that it does not emit, absorb, or interact with light or any other form of electromagnetic radiation in any known way. It cannot be seen. It cannot be detected by any conventional telescope or sensor. Its existence is inferred entirely from its gravitational effects on ordinary visible matter. The evidence for dark matter is overwhelming and comes from multiple independent lines of observation. It was first compellingly argued in the 1970s by the American astronomer Vera Rubin, who measured the rotation curves of spiral galaxies, the relationship between the orbital speed of stars and gas at different distances from the galactic center. In ordinary physics, if most of a galaxy's mass is concentrated at its center in the dense bulge of stars, then stars and gas at greater distances should orbit more slowly, just as the outer planets in the solar system orbit more slowly than the inner ones. This is simply Newton's law of gravity applied to galactic scales. It's what we see in the solar system. It's what we should see in galaxies. But Rubin found something profoundly different. The rotation curves of spiral galaxies are flat. Stars and gas at large distances from the galactic center, far out in the disk, and beyond orbit at roughly the same speed as stars closer in. They do not slow down as they should. This flatness of the rotation curve is inconsistent with the distribution of visible matter in the galaxy. The only way to explain it, within the framework of standard gravity, is to postulate that there is additional, invisible mass distributed throughout and around the galaxy in a roughly spherical halo, a dark matter halo that extends far beyond the visible disk. The dark matter halo of the Milky Way is thought to extend to distances of perhaps 300,000 to 1 million light-years from the galactic center, far beyond the stellar halo, far beyond the disk, far above and below the galactic midplane in every direction. Its mass is estimated to be several times greater than the total mass of all the visible stars, gas, and dust in the galaxy combined. By some estimates, dark matter constitutes roughly 85% of the Milky Way's total mass. The stars, gas, and dust that make up everything we've discussed, everything we can see, touch, measure, and observe, are a minor component of the galaxy's total mass budget. What is dark matter made of? This is one of the most profound open questions in physics and cosmology. Decades of dedicated experiments have failed to directly detect dark matter particles in terrestrial laboratories. Dozens of candidate particles have been proposed, tested, and ruled out or left unconfirmed. The weakly interacting massive particle, or WIMP, was for many years the leading candidate, a hypothetical particle with mass comparable to atoms, but interacting only through gravity and the weak nuclear force, making it essentially transparent to electromagnetic detection. Despite enormous experimental efforts, massive underground detectors filled with liquid xenon or germanium, sensitive enough to potentially detect single nuclear recoils, no confirmed WIMP detection has been made. Other candidates include Axion's extremely light particles originally proposed to solve a problem in quantum chromodynamics that also happen to have the right properties to be dark matter. Sterile neutrinos, hypothetical, heavier cousins of the known neutrinos that interact even more feebly with ordinary matter. Primordial black holes formed in the early universe that could constitute some or all of the dark matter through gravitational mass alone. None of these candidates has been definitively confirmed. Some physicists have proposed that dark matter doesn't exist as a particle at all, that instead, the gravitational force law itself is modified at large scales in ways that would explain the rotation curve observations without requiring any additional mass. This approach, known as modified Newtonian dynamics, or MOND, and more sophisticated versions of it in relativistic frameworks, has had some successes in explaining certain observations, but has struggled to account for the full range of evidence that supports dark matter, particularly observations of galaxy cluster collisions, where dark matter and ordinary matter appear to separate during the collision, and observations of the cosmic microwave background, which fit remarkably well with dark matter models. The honest answer is that we do not know what dark matter is. We are confident it exists, or that something must play its gravitational role in the universe. But its fundamental nature remains one of the deepest unsolved mysteries in science. What we do know is that the dark matter halo envelops the Milky Way, and by extension, our solar system in every direction, including dramatically above and below the galactic disk. Above the disk, below the disk, extending outward for hundreds of thousands of light years, the dark matter halo is the single largest structural component of our galaxy. It is the gravitational scaffolding upon which the visible galaxy, the stars, the gas, the dust, the spiral arms, is built. The dark matter halo is not perfectly uniform. Simulations of dark matter structure formation suggest that the dark matter in galaxy halos should be clumpy on small scales organized into subhalos, filaments, and voids within the larger halo structure. Some of these subhalos may be entirely devoid of ordinary matter, purely dark matter concentrations that have never attracted enough gas to form stars. Others may correspond to the dwarf satellite galaxies that orbit the Milky Way. The precise distribution of dark matter within and around our galaxy is still being mapped, with ongoing advances in gravitational lensing, stellar dynamics, and satellite galaxy surveys steadily improving our picture. Standing on Earth and looking upward, you are looking through the galactic disk, through the stellar halo, and into the outer reaches of the dark matter halo. You cannot see it. Your eyes detect no dark matter photons because there are none. Your instruments measure no dark matter signals because we have not yet found an instrument sensitive enough to detect them directly. Yet dark matter is there, above and below you, in incomprehensible quantities, shaping the galaxy that contains everything you know and everything you will ever know. The Milky Way does not exist in isolation. It is orbited by a collection of smaller galaxies, satellite galaxies, scattered through the halo in all directions, including dramatically above and below the galactic disk. These satellites range from the spectacular to the nearly invisible, from massive systems containing billions of stars to tiny, faint dwarf galaxies containing only a few thousand stars, barely distinguishable from an unusually rich globular cluster. The most famous of the Milky Way's satellite galaxies are the Large and Small Magellanic Clouds, two irregular dwarf galaxies visible to the naked eye from Earth's southern hemisphere, appearing as detached patches of the Milky Way in the constellations Dorado and Tucana. The Large Magellanic Cloud lies approximately 160,000 light-years away. The Small Magellanic Cloud is about 200,000 light-years distant. They are gravitationally bound to the Milky Way and are slowly being pulled toward it, their shapes distorted by tidal forces, their interstellar gas being drawn out into a great streaming structure called the Magellanic Stream, a ribbon of hydrogen gas that arcs across nearly 140 degrees of sky above the South Galactic Pole. The Magellanic Clouds are not quiet, passive satellites. The Large Magellanic Cloud, despite being roughly 1/100th the mass of the Milky Way, is an actively star-forming galaxy with a rich population of young blue stars, star-forming nebulae, and stellar clusters. The Tarantula Nebula, located within the Large Magellanic Cloud, is the most luminous and most active star-forming region in the entire local group of galaxies, a monstrous stellar nursery that, if located at the distance of the Orion Nebula, would cast shadows on Earth at night. In 1987, a star in the Large Magellanic Cloud exploded as a supernova, supernova 1987A, the closest and brightest supernova observed since the invention of the telescope, briefly visible to the naked eye in the southern hemisphere sky. The Milky Way has approximately 50 to 60 known satellite galaxies, and surveys continue to find new ones, mostly tiny, faint systems called ultra-faint dwarf galaxies that are barely distinguishable from the background noise of the stellar halo. Some of these satellites are thought to be among the most dark matter-dominated objects in the universe, small systems where the mass in dark matter exceeds the mass in visible stars by factors of hundreds or even thousands. They are, in a sense, dark matter halos that barely manage to gather enough ordinary matter to form any stars at all. The distribution of satellite galaxies around the Milky Way is not random. For reasons that are not fully understood, many of the known satellites appear to be arranged in a roughly planar distribution, a plane of satellites that is itself approximately perpendicular to the galactic disk. This alignment is puzzling in the context of standard dark matter cosmological models, which predict that satellites should be distributed more randomly in all directions. Whether this alignment represents a genuine physical structure perhaps the remnant of a group of galaxies that fell into the Milky Way together along a cosmic filament, or is simply a statistical artifact of incomplete surveys, is actively debated. The satellite galaxies orbit the Milky Way on paths that carry them above and below the galactic disk, plunging through it periodically over orbital timescales of hundreds of millions to billions of years. Each passage through the dense galactic disk can cause tidal disruption, stripping stars and gas from the satellite and potentially triggering star formation bursts through gravitational interaction. The Large Magellanic Cloud, by some calculations, will eventually merge with the Milky Way, probably in about 2.4 billion years. When it does, the collision will likely spark a new era of star formation, potentially disturb the outer regions of our galaxy significantly, and may even perturb the central supermassive black hole of the Milky Way, triggering a period of quasar-like activity. The satellite galaxies above and below the Milky Way are reminders that our galaxy exists not in isolation, but as part of a gravitationally bound community, the local group of galaxies. The Milky Way is one of roughly 80 known galaxies that form the local group, a gravitationally bound collection of galaxies spread across a volume approximately 10 million light-years in diameter. The local group is dominated by three large spiral galaxies: the Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy, also known as Messier 33. Around these three spirals orbit dozens of smaller, elliptical, irregular, and dwarf galaxies, the satellites and companions of the group's dominant members. The Andromeda Galaxy, also designated Messier 31, is the largest and most massive galaxy in the local group. Located approximately 2.5 million light-years from the Milky Way, Andromeda contains perhaps 1 trillion stars, roughly twice to 3 times the number in the Milky Way. It is the most distant object visible to the naked eye under dark sky conditions, appearing as a faint, elongated smudge in the constellation Andromeda. Knowing that this smudge is an entire galaxy containing 1 trillion stars and extending for 220,000 light-years, and that the light entering your eye when you see it left Andromeda 2.5 million years ago, when our Australopithecine ancestors were walking the African savanna, is one of the more mind-expanding experiences available to a human being standing outside on a clear night. Andromeda and the Milky Way are on a collision course. Measurements of Andromeda's velocity relative to the Milky Way confirm that the two galaxies are approaching each other at approximately 110 kilometers per second. The collision is projected to occur in approximately 4.5 billion years, coincidentally, roughly around the time the Sun will be entering the late stages of its red giant phase. The merger of the two galaxies, which will play out over hundreds of millions of years after the initial collision, will produce a giant elliptical galaxy, sometimes called Milkomeda or Milkdromeda. In popular accounts, very different in structure from either of the current spirals. In the cosmic collision, it is important to note the stars themselves are exceedingly unlikely to actually crash into one another. Galaxies, despite their enormous star populations, are mostly empty space. The average distance between stars, even in dense regions of the galactic disk, is measured in light years. The collision of two galaxies is primarily a gravitational event. The dark matter halos interpenetrate and merge. The gravitational potentials of the two galaxies distort and reshape each other, triggering enormous new waves of star formation as gas clouds are compressed by the collision's shock waves. The stars themselves drift past each other like two swarms of bees passing through each other. The galaxy is transformed, but individual stars survive. The local group itself is embedded in an even larger structure, but we'll reach that shortly. First, let's return to what happens directly above and below the Milky Way's own disk, in the space between our galaxy and its nearest neighbours. The intergalactic space within the local group, the space between the Milky Way and Andromeda, between the spirals and their satellite galaxies, is not purely empty. It contains extremely diffuse intergalactic gas, predominantly hydrogen, at very low densities. Some of this gas may form a warm-hot intergalactic medium that extends between the galaxies of the local group, and both the Milky Way and Andromeda are surrounded by extended coronae of hot gas halos of plasma that extend for hundreds of thousands of light years around each galaxy. The Milky Way's hot gas halo may itself extend to distances approaching the midpoint between us and Andromeda. Step back further, still far enough that the local group is just a cluster of points, the Milky Way and Andromeda, and their companions, indistinguishable from one another at the scale we're now viewing, and a vast new architecture comes into focus. The universe is not uniformly filled with matter. On the very largest scales, matter is organized into a structure often called the cosmic web, a network of immense filaments, sheets, and walls of galaxies surrounding vast, nearly empty regions called cosmic voids. This structure emerged from the quantum fluctuations of the very early universe, tiny differences in density that were stretched to cosmic scales during the period of rapid expansion called inflation, and then amplified over billions of years by gravity into the large-scale structure we observe today. The filaments of the cosmic web are the highways of the universe. They are vast streams of matter, dark matter, and ordinary matter, both that connect clusters of galaxies like the threads of an enormous three-dimensional spiderweb. Individual galaxies, groups, and clusters are concentrated along these filaments and at the nodes where filaments intersect. Between the filaments lie voids regions of dramatically lower galaxy density that can span hundreds of millions of light years. The local group, including the Milky Way, Andromeda, and their companions, is not located at a major filament node. We are a relatively modest collection of galaxies in a somewhat peripheral location relative to the nearest major structure in the cosmic web, the Virgo supercluster. The Virgo supercluster, also called the local supercluster, is a massive concentration of galaxy groups and clusters centered on the Virgo cluster, a dense collection of approximately 1,300 to 2,000 galaxies located roughly 53 million light-years from the bowed Ol the dense collection. Milky Way. The Virgo supercluster spans roughly 110 million light-years and contains the local group as one of its many constituent galaxy groups. The Virgo cluster itself is the dominant gravitational center of the supercluster, and the local group, along with other nearby galaxy groups, is slowly drifting toward it under its gravitational pull. But even the Virgo supercluster is not the highest level of this hierarchy. In 2014, a team of astronomers led by Brent Tully at the University of Hawaii redefined the boundaries of our cosmic neighborhood by mapping the motions of galaxies on even larger scales. By tracing the flow of galaxies toward their gravitational attractors, they identified a vast supercluster that encompasses the Virgo supercluster as just one region among many. They named this structure Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea is a supercluster of superclusters, a watershed region of gravitational flow in which galaxies are converging toward a common gravitational attractor called the Great Attractor. Laniakea spans roughly 520 million light-years and contains the equivalent of approximately 100,000 large galaxies or 100 million billion solar masses of matter. The Milky Way is located near the outer edge of Laniakea in the Virgo supercluster, near the boundary of the overall structure. Within Laniakea, the concept of above and below takes on yet another new meaning. These directions now reference the vast three-dimensional architecture of a supercluster region spanning 500 million light-years. The Great Attractor, the gravitational focus toward which much of the matter within Laniakea, including our own local group, is slowly flowing, is a diffuse concentration of mass in the region of the Norma cluster, roughly 250 million light-years from the Milky Way in the direction of the constellation Norma. The flow toward it is subtle by everyday standards. The local group is moving toward the Great Attractor at hundreds of kilometers per second, a motion that becomes apparent only when the peculiar velocities of galaxies across an enormous volume of space are carefully mapped. Beyond Laniakea, the universe continues other superclusters, other filaments, other nodes of the cosmic web, stretching outward for billions of light-years in every direction. The observable universe, the region from which light has had time to reach us since the Big Bang, spans roughly 93 billion light-years in diameter, though the full extent of the universe, if it is finite, may be vastly larger, or it may be infinite. In all of this, the question of what lies above and below the solar system has taken us from the icy debris of planet formation, through the sun's protective plasma bubble, through a cosmic void carved by stellar catastrophe, up through the spinning disk of a vast spiral galaxy, into the ancient stellar halo, through the invisible dark matter architecture, across intergalactic space, and into the large-scale structure of the universe itself. Throughout all of this exploration, one theme has appeared repeatedly. The solar system is not stationary. It is moving. It has always been moving. It will always be moving. And the direction of that movement and the speed places our above and below not in any fixed reference to the universe, but in a constantly shifting relationship to everything around us. The Sun and its planetary system orbit the Milky Way's center at approximately 515,000 miles per hour. The entire Milky Way, along with the local group, moves toward the Virgo cluster at roughly 150 miles per second. The local group as a whole participates in the broader flow of matter toward the Great Attractor. And on the very largest scales, the entire structure of Laniakea participates in the expansion of the universe itself, the general recession of everything from everything that has been happening since the Big Bang. At every scale, we are in motion. There is no cosmic rest frame. There is no fixed floor or ceiling. The above and below of the solar system change continuously as the solar system moves through the galaxy, oscillating above and below the galactic midplane, cutting through different regions of the interstellar medium, entering and exiting molecular clouds, crossing through density waves in the spiral arms. What this means, at a philosophical level, is that our position in the universe is not a fixed address. It is a trajectory, a path through space and time that has been ongoing for 4.6 billion years and will continue for billions more. The solar system has been to places literally that no human has ever known about because they happened long before humans existed. It has passed through denser regions of the galaxy and sparser ones, through different interstellar environments at different heights above and below the galactic midplane. The iron 60 inches the ocean sediments is just one trace of this journey, a geological record of a cosmic passage. The solar system will continue to move. In the future, it will oscillate through the galactic disk, potentially entering spiral arm regions of higher stellar density, potentially passing through molecular clouds that compress the heliosphere, potentially encountering different cosmic ray environments. In approximately 4.5 billion years, the Andromeda collision will dramatically alter the galactic environment and, presumably, the position and orbital trajectory of everything within it. none of this will be witnessed by any living thing currently on Earth. The timescales involved are so vast as to be entirely beyond direct human experience, but they are real. They are happening right now, slowly. We are moving through the galaxy at 500,000 miles per hour, tracing a great arc through the spiral disk, oscillating gently above and below the midplane, embedded in a web of structures that extends from the frozen edges of our own solar system to the largest scales of the observable universe. We have spent much of this journey mapping structures in the abstract distances, densities, temperatures, timescales. But there is another way to approach the question of what lies above and below the solar system, one that is perhaps more intimate and more viscerally compelling. What would you actually see if you could travel there? What would the universe look like from those perpendicular directions, rising out of the plane of the planets and looking back? Let us take that journey imaginatively, carefully, and in detail. Imagine you are standing on Earth. You look up. You are already looking, in a sense, partly above the ecliptic plane, depending on the time of year and the direction you face. The plane of the solar system cuts across the sky at various angles. The ecliptic is the invisible line along which the sun, moon, and planets all appear to travel. When you see Jupiter or Saturn or Venus in the night sky, they are always close to this line, never far from it, because you and they all live within the same thin disk. Now imagine you begin to rise, slowly at first. You climb out of the atmosphere, past the orbits of the ISS and the communications satellites, past the moon at 240,000 miles, past the increasingly faint glow of the zodiacal light, the sunlight scattered by dust that lies within the plane of the solar system, tracing the ecliptic in a faint column of brightness before dawn and after dusk. This zodiacal light is one of the most direct visual manifestations of the solar system's flat structure. It marks the disk of dust in the same plane as the planets, and as you rise above it, it flattens from a column into a thin line and then fades into the background. At a few AU above the ecliptic plane, the view begins to change in profound ways. Looking down back toward the plane, you begin to see the solar system as it truly is, a flat disk, exactly as those textbook diagrams showed, but now from the outside, from above. The sun blazes at the center. The planets are invisible at this distance, too small, too faint, too far separated from one another. But the diffuse glow of the zodiacal dust disk is still faintly visible, a thin plane of scattered light extending outward from the sun in all directions within the ecliptic. The sky above you, the direction you've been traveling, is not empty. It looks empty because the stars visible in that direction are essentially the same stars visible from Earth, just unfiltered by atmosphere. But there are more of them than you could ever see from Earth's surface. The atmosphere absorbs and scatters light, limiting ground-based naked eye visibility to stars of about 6th magnitude. Out here, with no atmosphere, the sky is deeper and more detailed. Every direction offers stars, faint and bright, old and young, the ancient light of suns scattered across thousands of light years in every direction. As you rise further hundreds of AU now, well beyond the Kuiper belt, approaching the inner edge of the Oort cloud, the solar system behind you has vanished. The sun is just another star bright by comparison with other nearby stars, but a star nonetheless, a point of light rather than a disk, its light no longer enough to overwhelm the darkness. The planets are gone entirely, their reflected light too faint to detect. In every direction, the sky is the same, stars, darkness. The faint smear of the Milky Way cutting across the sky, not a band you see above you or below you from some surface, but a band that now cuts across your field of view at an angle depending on which direction you face. Remember that tilt the solar system is inclined 60 degrees relative to the galactic disk. From your vantage point above the ecliptic, the galactic plane doesn't align with the direction you've been traveling. It cuts across the sky at an angle, more concentrated in some directions, fading toward the galactic poles in others. At this distance, the Oort cloud surrounds you. You can't see it. Individual Oort cloud objects kilometers to tens of kilometers in size, pitch black, far from the sun, are far too faint and too separated to detect with the naked eye, even from within the cloud itself. The space you're traveling through looks completely empty, but it isn't. You are surrounded by trillions of frozen bodies, drifting in the darkness on their immense, slow orbits, indifferent and silent. The journey outward through the Oort cloud takes a long time, even at tremendous speeds. Thousands of AU pass, tens of thousands. The sun grows fainter until it is simply one of the brightest stars in the sky, brighter than Sirius appears from Earth, but not dramatically so. Our nearest neighbour, the Alpha Centauri system, is now visible as a bright star in a different part of the sky. The distances between stars make them look close together, even when they are light years apart. Eventually, if you could travel far enough in a short enough time, the last faint gravitational tendrils of the sun's Oort cloud are behind you. You are in interstellar space. You are, in a technical sense, no longer within the solar system. You are between the stars. The view here is one of absolute, overwhelming darkness, punctuated by the ancient light of distant suns. In every direction, stars. No sun nearby, no planet, no dust. Just the interstellar medium invisible hydrogen and helium at near perfect vacuum densities and the stars. Now you rise further, in the direction perpendicular to the galactic disk. The Milky Way band, which had been cutting across your sky at an angle, slowly shifts as you ascend. The stars of the galactic disk become more concentrated in a ring around your sky, and then, as you rise high enough above the disk, that ring narrows and brightens below you. You are climbing out of the disk. The dense, complex, bright plane of the Milky Way is now the floor beneath you, a brilliant band of light spread in a great ring at lower angles in your sky. Above you, directly above, in the direction perpendicular to the galactic plane, the stars thin out rapidly. You are now in the galactic halo, and halo stars are sparse. The sky in the direction you're traveling is darker, emptier, more primal. But it is not empty. Scattered across that dark sky are the brilliant, symmetric, jewel-like points of light of the globular clusters, dozens of them visible now, no longer lost in the rich background of the disk, standing out clearly against the darkness. Each one is a compact sphere of hundreds of thousands of ancient stars, orbiting the galactic center on long looping paths that carry them above and below the disk. Looking back down toward the galactic disk now far below you, you begin to see the Milky Way as something external for the first time. It is not a band across your sky anymore. It is a structure below you, a magnificent, impossibly detailed flat galaxy spread out beneath you like a vast luminous carpet. Spiral arms trace outward from the central bar in sweeping curves. The thick central bulge glows with the warm amber light of billions of old stars. The disk is populated with blue-white star-forming regions, dark lanes of dust, and the diffuse glow of billions of unresolved stellar points. You cannot see dark matter, but you know it's there. The galaxy you're looking at is embedded in a vast, roughly spherical cloud of invisible mass that extends far beyond the visible disk in every direction, including the direction you're currently traveling. The disk you're seeing is just the luminous tip of an iceberg, the small fraction of the galaxy's total mass that has condensed into stars and gas clouds dense enough to emit or reflect light. At distances of tens of thousands of light years above the disk, the satellite galaxies become visible, small, faint, irregular patches of light orbiting the Milky Way at various distances. The Magellanic Clouds, if you're oriented correctly, shine as bright, detached patches larger and more detailed at this distance than they appear from Earth, because you're now viewing them from outside rather than from within the disk at a foreshortened angle. At hundreds of thousands of light years above the disk, the entire Milky Way is laid out beneath you in its full glory. At this distance, the satellite galaxies are small companions orbiting a magnificent spiral. The disk is perhaps 100,000 light years in diameter. As seen from this altitude, a vast, luminous structure that is simultaneously the entire context of our solar system and a tiny, insignificant speck on the scale of the universe. This is the view that lies above and below our solar system, not just the icy debris and the protective bubbles of the inner layers, but ultimately, if you travel far enough, the entire magnificent architecture of the galaxy itself. One of the greatest challenges in understanding everything we've discussed is the sheer incomprehensibility of the scales involved. Human beings evolved to navigate spaces measured in meters and kilometers. We can intuitively grasp a room, a city, a country. We can stretch our intuition somewhat further to grasp a planet, or even the distance from Earth to the Moon. But the distances that define the structures above and below the solar system, the Oort cloud, the local bubble, the galactic halo, are so far beyond everyday intuition that any attempt to grasp them directly fails. So let us try a different approach. Let us compress the scales into something that can be compared and contrasted in a single, continuous chain of reference. Start with the Earth. Our planet is approximately 12,742 kilometers in diameter. At this scale, you are standing on a ball roughly the size of a standard globe in a classroom. The Moon, at an average distance of 400 kilometers, is about 30 Earth diameters away, close enough that on the classroom globe scale, the Moon would be within the same room. Now, compress everything by a factor of 1,000,000. In this scale, 1 kilometer in our model represents 1,000,000 kilometers in reality. The Earth is now about 12.7 millimeters in diameter, the size of a grape. The Moon is about 38 centimeters away within arm's reach. The Sun, at 150 million kilometers from Earth, is now about 150 meters away, about half the length of a city block. At this scale, the solar system begins to reveal its emptiness. Neptune, the outermost planet, orbits at roughly 4.5 billion kilometers from the Sun in our model, about 4.5 kilometers away from our basketball-sized sundae. The entire planetary solar system, from Mercury to Neptune, fits within a sphere about 9 kilometers in diameter. At this scale, the Sun is roughly the size of a small car. Earth is a grape 150 meters away. Neptune is a marble 4.5 kilometers away. Now continue outward. The Kuiper belt extends to about 50 AU in our model, about 7.5 kilometers from the sundae. The heliopause, where Voyager 1 crossed into interstellar space, is at roughly 120 AU, about 18 kilometers from our model sundae, still within the same city. But the inner edge of the Oort cloud is at 2000 AU in our model, 300 kilometers away. That's the distance from one major city to another. The outer edge of the Oort cloud, at perhaps 100,000 AU, is in our model 15,000 kilometers away, a third of the way around the Earth. And the nearest star system, Alpha Centauri, at 4.24 light years. At 1 million to 1 scale, Alpha Centauri is approximately 40 million kilometers away, a quarter of the distance from Earth to the Sun in real space. Our scaled model now requires a model that extends from here to the Sunday. Clearly, even 1,000,000 to 1 compression isn't enough. Let us add many more zeros. The local bubble spans roughly 1,000 light-years, about 9.5 quadrillion kilometers. The Milky Way disk is 100,000 light-years across nearly 1,000,000 quadrillion kilometers. The distance to Andromeda is 2.5 million light-years. Laniakea spans 520 million light-years. The numbers become meaningless in any direct intuitive sense. But the chain of structures is real. Each one exists, extends above and below us in 3 dimensions, and has been verified through careful observation and physical reasoning. The emptiness between them is not a failure of our models. It is a real feature of the universe. Space is overwhelmingly and profoundly empty, and yet it is not boring. In that emptiness, there is dark matter threading through everything in invisible filaments. There are gravitational waves rippling outward from merging black holes and neutron stars. There is the cosmic microwave background, the afterglow of the Big Bang bathing every point in space with a whisper of ancient radiation. There are neutrinos passing through everything at the speed of light, trillions of them passing through your body every second without interacting with a single atom. There are magnetic fields threading through the interstellar medium, the galactic disk, and the intergalactic space between galaxies. The emptiness is populated, the darkness is structured, and the structures above and below our solar system are part of a web of organization that extends from the smallest scales of particle physics to the largest scales of cosmic architecture. The position of the solar system within the Milky Way is not arbitrary. While there is no evidence that the solar system was placed here by design, there are compelling reasons why a solar system supporting complex life would be more likely to arise in a location like ours than in many other regions of the galaxy, and those reasons are intimately tied to what lies above and below different regions of the galactic disk. The concept of a galactic habitable zone mirrors the more familiar concept of a stellar habitable zone, the range of distances from a star at which liquid water can exist on a planetary surface. The galactic habitable zone is the region of the galaxy where conditions are most favourable for the development of complex life. It's a rough and somewhat controversial concept, but it captures something real about the relationship between galactic structure and planetary habitability. Near the galactic centre, conditions are hostile to complex life in several ways. Stellar density is orders of magnitude higher than in our region of the galaxy. Stars are crowded together, and the probability of close stellar encounters close enough to gravitationally disrupt planetary orbits or shower a planetary system with comets is dramatically higher. Supernova rates are higher near the galactic centre, meaning the flux of lethal radiation reaching planetary surfaces is higher. The galactic centre also hosts Sagittarius A times the Milky Way's central supermassive black hole, roughly 4 million times the mass of the Sun, which periodically flares with energetic activity, as well as an enormous population of neutron stars, magnetars, and stellar mass black holes that make the central parsecs of the galaxy an extremely energetically active and hostile environment. Far out in the outer disk and halo, conditions present a different kind of problem. Stars in the outer disk and halo tend to be metal poor, deficient in the heavy elements that are essential for building rocky planets and for chemistry complex enough to support life. Carbon, oxygen, nitrogen, phosphorus, iron, silicon, all the elements that make up the bodies of living organisms and the surfaces of habitable planets are produced in stars and distributed through the interstellar medium by supernova explosions. Regions of the galaxy that have experienced less stellar evolution and fewer supernovae, the outer disk, the halo have lower abundances of these essential elements. The probability of forming Earth-like rocky planets in such regions is correspondingly lower. The solar system's position, roughly 26,000 light-years from the galactic center, in the middle disk between the inner crowded zone and the outer metal-poor regions, is in the approximate range of the galactic habitable zone. It's neither too close to the violent center nor too far from the metal-rich regions where rocky planets can form. It's in a relatively calm inter-arm region rather than in the middle of a spiral arm, where stellar density, star formation rate, and supernova frequency are all higher. The solar system's height above the galactic midplane also matters. Being close to the midplane within the thin disk means the Sun is bathed in the full stellar density environment of the disk, with its associated star formation, molecular clouds, and supernova activity. Being far above or below the midplane in the thick disk or halo would mean lower metallicity and a very different cosmic ray and gravitational environment. The Sun's current position, about 56 light-years above the galactic midplane, well within the thin disk, but not at the densest part of it, is again approximately optimal within the range of parameters that favour complex planetary systems. This is not to say that life is impossible in other regions of the galaxy. The universe is vast, and the diversity of potentially habitable environments almost certainly exceeds our ability to predict from first principles. But the conditions that allowed the Sun's formation with the right metallicity, that allowed Earth to form with the right composition, that maintained a stable planetary environment for billions of years, while life evolved from single-celled organisms to the complex biosphere, we know these conditions are more likely to be found in a region like ours than in the galactic center or the outer halo. What lies above and below our solar system is, in this sense, not just a matter of curiosity. It is directly relevant to the question of why we are here at all. Among the most tangible ways in which what lies above and below the solar system affects life on Earth is through cosmic rays, high-energy charged particles that stream through the galaxy in all directions, including from directly above and below the ecliptic plane and the galactic disk. Cosmic rays are not rays in the conventional sense. They are subatomic particles, mostly protons, but also atomic nuclei, electrons, and positrons, accelerated to extraordinarily high energies by various astrophysical processes. The most energetic cosmic rays carry kinetic energies that are, for a single subatomic particle, incomprehensibly large. Some have been measured with energies exceeding 10 to the power of 20 electron volts, which corresponds to the kinetic energy of a cricket ball moving at about 100 kilometers per hour, concentrated into a single proton. These ultra-high energy cosmic rays are rare, but they represent some of the most energetic individual particles ever detected. Most cosmic rays originate within the Milky Way and are accelerated by supernova remnants, the expanding shock waves left behind after massive stars explode. As these shock waves expand through the interstellar medium, they can trap charged particles and accelerate them to extraordinary energies through a process called diffusive shock acceleration. The particles bounce back and forth across the shock front, gaining energy with each crossing until they reach energies high enough to escape the magnetic confinement of the remnant and stream freely through the galaxy. Cosmic rays travel through the galaxy's magnetic field, which deflects their trajectories and scrambles their directions. By the time they reach the solar system, the directions from which they arrive are almost completely randomized. They come from above, below, left, right, ahead, behind, in equal quantities from all directions. This isotropy makes it nearly impossible to trace cosmic rays back to their sources except at the very highest energies, where the magnetic deflection is small enough that some directional information survives. The galactic magnetic field extends above and below the disk, threading through the halo in a complex, turbulent pattern that confines cosmic rays within the disk for millions of years before they diffuse outward and escape into intergalactic space. The typical cosmic ray proton bounces around in the galactic magnetic field for roughly 10 million years before leaving the galaxy. During this time, it may traverse the full thickness of the disk multiple times, rising above and below the midplane on chaotic, magnetically deflected trajectories. When cosmic rays reach the solar system, they encounter the heliosphere's magnetic field, which provides some additional deflection and attenuation, more effective for lower energy particles, less effective for higher energy ones. The most energetic cosmic rays penetrate the heliosphere with essentially no deflection. Lower energy cosmic rays are significantly modulated by the heliosphere, with their flux at Earth varying with the solar activity cycle. When cosmic rays enter Earth's atmosphere, they collide with nitrogen and oxygen nuclei, producing cascades of secondary particles, pions, muons, electrons, photons, neutrinos that shower downward through the atmosphere in great particle avalanches called extensive air showers. The muons produced in these cascades are remarkably penetrating, capable of traveling through hundreds of meters of rock before being stopped. Right now, as you read this, thousands of muons are passing through your body. Every minute cosmic particles produced in the upper atmosphere by the collision of protons that may have been accelerated in supernova remnants thousands of light years above and below the plane of the galaxy. The biological effects of cosmic rays are a subject of ongoing research. At Earth's surface, the background radiation from cosmic rays contributes a meaningful fraction of the natural radiation dose received by humans, comparable to or slightly less than the dose from radon gas. At high altitudes in aircraft, at mountaintops, the cosmic ray dose is significantly higher because less atmospheric shielding is available. Astronauts in deep space, outside the protection of both the heliosphere and Earth's magnetic field, receive cosmic ray doses many times higher than those at Earth's surface. Over geological timescales, cosmic ray flux at Earth's surface has varied significantly. When the solar system passes through denser regions of the galactic disk closer to spiral arms, or during periods when nearby supernovae are more frequent, the cosmic ray flux can increase substantially. Some researchers have proposed that these variations in cosmic ray flux may have influenced Earth's climate through effects on cloud formation and atmospheric chemistry, and may have influenced the pace of mutation and evolution by altering background radiation levels. These hypotheses are intriguing but remain controversial and not yet firmly established. What is not controversial is that cosmic rays are a real, measurable, and important feature of the environment above and below the solar system. They are, in a very literal sense, the galaxy reaching down and touching us particles launched by stellar deaths thousands of light years away, accelerated to nearly the speed of light, and raining down on our planet from every direction, carrying in their energy signatures and compositions the fingerprints of astrophysical processes operating on cosmic scales. Among the most underappreciated structures that exist above and below the solar system are the magnetic fields that thread through the interstellar medium, the galactic disk, and the galactic halo. They are invisible, undetectable to the unaided senses, and yet they shape the behavior of charged particles, the dynamics of star formation, and the structure of cosmic ray propagation throughout the galaxy. Magnetic fields pervade the Milky Way at every scale. Within the solar system, the Sun's magnetic field extended outward by the solar wind forms the heliospheric magnetic field, a vast spiral structure that rotates with the Sun and fills the entire heliosphere. The direction of this field reverses with every solar cycle, alternating between pointing inward and outward with an 11-year periodicity. Beyond the heliopause, the interstellar medium carries its own magnetic field, the local interstellar magnetic field, with a characteristic strength of a few microgauss. This is extraordinarily weak by any terrestrial standard, roughly 10 billion times weaker than a typical refrigerator magnet. Yet, on the scales of interstellar space, this weak field is enormously influential, guiding the flow of cosmic rays, affecting the dynamics of gas clouds, and shaping the overall structure of the interstellar medium. The galactic magnetic field is structured on multiple scales. On large scales, it follows the spiral arms of the galaxy, tracing a roughly coherent pattern that mirrors the galaxy's overall structure. On intermediate scales, the field is turbulent and complex, wound and tangled by the motions of the interstellar medium and the explosive energy injections of supernovae. On small scales, the field threads through individual molecular clouds and star-forming regions, playing a crucial role in regulating the rate of star formation by providing magnetic pressure support against gravitational collapse. Above and below the galactic disk, the magnetic field structure changes character. Within the disk, the field is predominantly parallel to the disk plane it runs along the spiral arms and through the interarm regions in a relatively organized way. But above and below the disk, the field begins to develop a more vertical, perpendicular component field lines that point away from the disk plane, rising into the halo like the bristles of a brush. These vertical field components are thought to be generated by the combined effect of supernova-driven outflows, which carry magnetized plasma upward from the disk into the halo. The galactic halo magnetic field is weaker and less organized than the disk field, but it extends to great heights above and below the disk, thousands of light years or more. It plays an important role in confining cosmic rays within the galaxy and in shaping the overall energetics of the galactic wind, the slow outflow of hot, magnetized plasma that streams out of the galactic disk in all directions, powered by the collective energy input of supernovae, stellar winds, and the turbulent disk environment. The interaction between the Milky Way's magnetic field and the intergalactic medium is a frontier of current research. The intergalactic medium itself carries magnetic fields extraordinarily weak, perhaps 10,000 times weaker than the already faint galactic field, but present over vast distances. The origin of these intergalactic magnetic fields is one of the outstanding puzzles of modern cosmology. They may represent the seeds from which galactic magnetic fields grew through amplification processes, or they may themselves be the product of magnetized outflows from early galaxies. What all of this means for the question of what lies above and below our solar system is that the vertical direction perpendicular to the ecliptic, pointing up and away from the plane of the planets, is not a direction of simple, featureless emptiness. It is threaded by magnetic fields, bathed in cosmic rays, populated by ancient stars on looping halo orbits, filled with the invisible mass of dark matter, and structured by the forces that have shaped the galaxy over billions of years. One of the more dramatic phenomena associated with the vertical direction in galaxies, the direction above and below the disk, is the galactic wind. Just as the Sun exhales a solar wind, a continuous stream of charged particles flowing outward from the corona, the Milky Way exhales a galactic wind, a large-scale outflow of hot gas, cosmic rays, and magnetic fields that streams out of the galactic disk above and below the midplane, rising into the halo and eventually escaping into the intergalactic medium. The galactic wind is powered by the collective energy output of the disk's stellar population. Supernovae, stellar winds from massive stars, and the turbulent energy of star-forming regions all contribute to the overall energy budget that drives material upward out of the disk. The individual supernova explosions we discussed in the context of the local bubble are, from this perspective, local manifestations of the larger process that drives the galactic wind globally. Hot gas plasma, heated to tens of millions of degrees by supernovae, rises buoyantly out of the disk, carrying with it metals produced by stellar nucleosynthesis, magnetic field lines dragged upward by the flowing plasma, and cosmic ray particles that are partially confined by those magnetic fields and transported with the outflow. This material rises into the halo, where it gradually cools and may eventually fall back down to the disk, a galactic scale circulation, sometimes called the galactic fountain. The galactic fountain model proposes that gas flows out of the disk above and below, rises into the lower halo to heights of a few thousand light years, cools and condenses into clouds of cold hydrogen, and then falls back down to the disk under gravity. The infalling clouds can trigger new episodes of star formation when they impact the disk, compressing existing molecular clouds and seeding new ones. The galactic fountain is thought to be one of the key mechanisms regulating the overall rate of star formation in the Milky Way. Some fraction of the galactic wind escapes entirely the most energetic, most tenuous component that reaches high enough velocities to exceed the escape velocity of the galaxy and flow out into the circumgalactic medium and beyond. This escaped material metals, cosmic rays, and magnetic fields enriches the intergalactic medium with elements that were produced inside stellar interiors. Over cosmic time, this process of galactic outflows has progressively enriched the intergalactic medium with heavy elements, spreading the products of stellar nucleosynthesis far beyond the boundaries of the galaxies where they were produced. The Milky Way's galactic wind is less dramatic than the winds observed in actively star-forming or starburst galaxies, where star formation rates are much higher and the collective energy of star formation drives powerful, galaxy-scale superwinds that can be observed directly as broad outflows of X-ray and infrared emission. But our galaxy's wind is real and ongoing, a continuous slow exhalation of material above and below the disk that has been operating throughout the Milky Way's history. Standing on Earth and looking upward, you are looking in the direction from which this galactic wind has been flowing for billions of years, a slow, invisible breath of hot plasma, rising from the disk of a vast spiral galaxy, carrying with it the elemental products of stellar evolution, spreading the chemistry of stars into the emptiness above and below. We have mentioned multiple times that the Sun oscillates above and below the galactic midplane as it orbits the galaxy. Let us now examine this oscillation more carefully, because it is one of the most fascinating and consequential aspects of the solar system's motion through the galaxy. The Sun's orbit around the galactic center is not a perfect flat circle. It is slightly elliptical, and it is additionally modulated by a vertical oscillation, a periodic bobbing motion perpendicular to the galactic midplane. As the Sun orbits the galactic center, it simultaneously rises above the midplane, reaches a maximum height, falls back through the midplane, descends below it, reaches a minimum height, and then rises back through the midplane again. This complete vertical oscillation takes approximately 60 to 70 million years. The restoring force that drives this oscillation is the gravitational pull of the galactic disk itself. When the Sun rises above the midplane, the gravitational attraction of the mass concentrated in the disk stars, gas, dark matter, pulls it back downward. The Sun overshoots the midplane due to its inertia, descends below it, and is then pulled back upward. It is, in the most precise mathematical sense, a simple harmonic oscillation driven by the gravitational field of the disk, though modified by the non-uniform distribution of mass and by the effects of encounters with massive objects like molecular clouds. The current position of the Sun, approximately 56 light-years above the midplane, and its current velocity in the vertical direction indicate that it recently crossed the midplane, heading upward, and is currently in the ascending phase of its oscillation. It will reach a maximum height of perhaps 200 to 260 light-years above the midplane in roughly 14 million years, then begin its descent, cross the midplane again in roughly 30 million years, reach a maximum depth of similar magnitude below the midplane, and rise back through the midplane again in about 60 to 70 million years total. This vertical oscillation is the solar system's participation in the Milky Way's own internal dynamics, the ripples and waves that propagate through the galactic disk and influence the distribution and behavior of its stellar populations. There is a long-standing and periodically revived hypothesis that the solar system's vertical oscillation may correlate with periods of increased biological extinction on Earth. The idea is this: when the Sun passes through the denser regions near the galactic midplane, where molecular cloud density is highest, the probability of a gravitational encounter with a dense molecular cloud increases. Such encounters could gravitationally perturb the outer solar system, disrupting the Oort cloud and sending showers of comets into the inner solar system. An increased rate of large comet impacts on Earth could trigger mass extinctions. Some analyses of the geological record have found periodicities in extinction rates, cycles of roughly 26 to 30 million years that approximately match the frequency of galactic midplane crossings. The Permian-Triassic extinction, the Cretaceous-Paleogene extinction that killed the non-avian dinosaurs, and several other mass extinction events have been examined in this context. However, the statistical evidence for a periodic signal in extinction data is debated. The orbital models for the Sun's galactic motion carry significant uncertainties, and the causal chain from molecular cloud encounter to comet shower to mass extinction is not firmly established. What is not debated is that the solar system's vertical position within the galactic disk changes over geological timescales, and that this changing position influences the cosmic environment experienced by Earth, the density of interstellar material the heliosphere must push against, the cosmic ray flux modulated by the surrounding stellar environment, and the probability of gravitational encounters with the dense features of the galactic disk. Our planet is not isolated from the galaxy. It is embedded in it, and the galaxy's structure leaves its mark on Earth's geological and biological record. The structures above and below the solar system are not just spatial features, they are also temporal ones. They encode the history of the universe in their compositions, their ages, their spatial distributions, and their motions. Looking upward from the plane of the solar system through the disk into the halo toward the ancient stellar populations that inhabit the vertical direction of the galaxy is, in a profound sense, looking backward in time. The most ancient stars in the galactic halo formed when the universe was young, perhaps 300 to 600 million years after the Big Bang. At that epoch, the universe was very different from today. It was smaller. The expansion of the universe means that the same volume of space was compressed into a smaller region in the past. It was hotter. The average temperature of the universe decreases with expansion. And it was less chemically complex. The universe was composed almost entirely of hydrogen and helium, with trace amounts of lithium produced in the Big Bang itself. All other elements had yet to be created. The first stars, astronomically designated as population 3 stars, were unlike any stars that exist today. They formed from purely primordial gas with essentially no heavy elements. Without carbon, oxygen, or other metals to act as efficient coolants in collapsing gas clouds, the first stars likely formed with much higher masses than typical stars today. Some models suggest population 3 stars may have been tens or hundreds of times the mass of the Sun brilliant, blue-white objects that burned through their nuclear fuel in only a few million years before exploding as supernovae or collapsing directly into black holes. These explosions were the first in the universe to produce and distribute heavy elements. The supernovae of population 3 stars seeded the surrounding gas with carbon, oxygen, neon, magnesium, silicon, sulfur, iron, and dozens of other elements, the raw material for the next generation of stars designated population 2. Population 2 stars formed with these newly available metals, though still with lower metallicity than modern stars. Many of the stars in the galactic halo today are population 2 stars, ancient, metal, poor, and scattered through the halo on the chaotic orbits characteristic of the early galaxy. The Sun is a population I star, a third-generation star, formed from gas that had already been enriched by the deaths of multiple previous generations. The heavy elements in the Sun, the iron, silicon, oxygen, carbon, and all the other elements that make up the planets and our own bodies are recycled stellar material produced in the nuclear furnaces of stars that lived and died long before the solar system formed. When we look above the galactic disk toward the halo stars, those old, metal-poor, ancient population 2 objects drifting on their high inclination orbits, we are looking at the survivors of the universe's second generation of stars. They have been burning for 12 to 13 billion years. They were old before the Earth existed. They were ancient before the Sun was born. They have watched the Milky Way assemble, evolve, and develop over essentially its entire history. The composition of halo stars, measured through spectroscopy, provides some of the most direct observational evidence for the Big Bang nucleosynthesis model and for the theory of stellar nucleosynthesis. By measuring the ratios of different elements in halo stars of different ages, tracing how the heavy element content of the universe has built up over time, astronomers can reconstruct the chemical evolution of the galaxy and, through it, the history of star formation and stellar death across cosmic time. The vertical direction of the galaxy above and below the flat disk is in this sense a direction that points toward the past. The farther above the disk you look, the older the stellar population you encounter. The globular clusters are among the oldest bound structures in the universe. The ancient halo stars are relics of conditions that prevailed billions of years before any complex chemistry was possible. And above all of this, in the cosmic microwave background that fills the universe in every direction, is the most ancient light of all the radiation released 380,000 years after the Big Bang, when the universe first became transparent, carrying across 13.8 billion years of cosmic time, a snapshot of the universe in its infancy. We began with a simple question: what lies above and below the solar system? The question seemed modest, almost trivial, a footnote to the standard diagrams of 8 planets orbiting a yellow star. The answer has taken us on a journey from the icy debris fields of the solar system's formation through the bubble of solar wind that protects our planetary family across the boundary into interstellar space, through a cosmic void carved by ancient stellar catastrophes, up through the rotating disk of a vast spiral galaxy, into the ancient stellar populations of the galactic halo, across intergalactic space to the satellite galaxies and companion spirals of the local group, and outward to the filaments and superclusters of the cosmic web. At every scale, the vertical direction opened onto new structure, new history, new physics. Nothing was empty, nothing was featureless, everything was connected. The solar system, seen from this perspective, is not an isolated object floating in a featureless void. It is a node in a network of structures that extends from the smallest debris of planet formation to the largest architecture the universe has assembled. It is embedded in a galaxy that is itself embedded in a group of galaxies, itself embedded in a supercluster, itself part of a cosmic web that covers the entire observable universe. And the fact that the solar system is tilted, that our flat disk of planets is inclined 60 degrees to the galactic plane, means that the above and below of our local frame does not align with the above and below of the galactic frame. Our perpendicular directions point partly into the galactic disk and partly out of it, making every direction simultaneously a local reference and a cosmic one, layered with structures at different scales, different ages, different temperatures, different densities. The structures above and below the solar system affect us in concrete, measurable ways. The cosmic rays that rain down from the galactic halo contribute to the radiation environment that has driven mutation and evolution on Earth. The dark matter halo shapes the gravitational environment through which the solar system travels. The heliosphere, extended above and below the ecliptic, shields our planetary system from the worst of the interstellar particle environment. The galactic disk's oscillations carry us through varying environments that may have left traces in the geological record. We are not outside these structures, observing them from a safe distance. We are inside them. We are part of them. The iron in our blood was forged in ancient supernovae and scattered through the interstellar medium before being incorporated into the solar nebula. The hydrogen in our water was produced in the Big Bang. The calcium in our bones, the oxygen we breathe, the carbon in every molecule of every cell, all of it was processed through stellar interiors, scattered by stellar winds and supernova explosions, and collected into the forming solar system. We are, in the most literal chemical sense, made of the structures above and below us. The textbook image of the solar system, 8 planets on a flat disk orbiting a yellow star, is not wrong. It is simply incomplete. It shows the furniture of a room without showing the room, the building, the street, the city, the continent, the planet, the atmosphere. The real solar system exists embedded in layer upon layer of structure, connected to the galaxy at every level, and connected through the galaxy to the full history of the universe. Above and below the plane of the planets lies the full architecture of everything that has ever existed and everything that will ever be, from the frozen relics of solar system formation to the ancient stellar survivors of the fall on BD. Universe's first billion years, from the invisible dark matter that holds the galaxy together to the cosmic microwave background that fills all of space with the afterglow of creation. The question of what lies above and below our solar system is, in the end, the question of what the universe is made of, how it got that way, and what our place in it truly is. And the answer is more than we imagined, more than we can fully comprehend, more than any diagram has ever captured. But we keep looking, we keep measuring, we keep sending spacecraft across the heliopause and analysing the iron isotopes in ocean sediments and mapping the stellar streams in the galactic halo and hunting for dark matter in deep underground laboratories. The structures above and below us are not just objects of curiosity, they are the pages of a history book that stretches back 13.8 billion years, written in the language of physics, chemistry, and light. And we are only just beginning to read it.